First law of thermodynamics. In the previous section, we learned that the internal energy of a system may change via two modes of energy transfer, heat and work. Let delta Q be the heat supplied to the system by the surroundings, delta W be the work done by the system on the surroundings, and delta U be the change in the internal energy of the system. Then, from the general principle of conservation of energy, we have delta Q equals delta U plus delta W. What this equation means is that the energy supplied to the system by the surroundings leads partly to change in internal energy of the system, while the rest is used up to do work on the surroundings. We can rewrite this equation as delta Q minus delta W equals delta U. Consider a gas changing states going from state P1V1 to P2V2. For this to happen, we may first change the volume of the gas, keeping the pressure constant, and move to P1V2, and then vary the pressure keeping the volume constant and move to P2V2. Another way to do this would be to first keep the volume constant and vary the pressure, and then keep the pressure constant and vary the volume. Since delta U is a state variable, its value depends only on the final state of the system. However, the values of delta Q and delta W may depend on the path taken by the system while getting to its final state. We also know that the value of delta Q minus delta W is path independent. So, if a system is taken through a process in which delta U equals 0, then delta Q minus delta W equals 0, or delta Q equals delta W. This implies that heat provided to the system by the surroundings is used up entirely by the system to do work on the surroundings. Consider the gas in piston arrangement we used earlier. Work done by the system against a constant pressure P is given by delta W and P delta V, where delta V is the change in volume of the gas. From the first law of thermodynamics, thus, delta Q equals delta U plus P delta V.